nature has crowded so many protons and neutrons into the nucleus that it becomes unstable. Finally, it throws out a small fragment, and in this way, radioactive rays are born. These rays cannot be seen, heard, or felt. The Geiger counter is used to detect their presence. It gives off audible clicks when the rays pass through it. And there is another instrument which even makes the rays visible to the naked eye. This special device is called a cloud chamber. It contains a tiny bit of radium which gives off a constant shower of atomic fragments. Of course, the fragments themselves are much too small to be seen, but you can now see their trails. Each new vapor trail shows that another atom has thrown off a fragment. Each atom does this only once in its entire life, but there are so many atoms that this activity is going on almost endlessly. We might say that a radioactive atom is like a set mousetrap. Both contain energy. The traps on this table represent the atoms in a piece of radium. Every so often one breaks down all by itself, releasing a bit of energy. But radium is useless as a power source. There aren't enough atoms releasing their energy at the same time. But nature knows all the secrets of the atom. Since the beginning of time, she has used atomic energy to power the whole universe and to light the fires in the sky. The best example is our own sun. These are actual time-lapse pictures of the sun's rim. That vast display of energy comes from an atomic fire raging deep in the core of the sun. If this was an ordinary fire, the sun would burn to a dead heap of ashes within a few thousand years. But so much energy is produced by these atoms that the sun will go on shining for billions of years to come. For a long time, nature alone knew how to open the vessel that contained this mighty force. To man, however, the vessel remained closed. Finally, he discovered the secret of how to open the vessel himself. The fisherman used his knife, and man, too, found a tool that broke the seal. The year was 1938. The place, Berlin, Germany. The leading character, that strange metal, called uranium. Again, it turned out to be the star of a sensational scientific discovery. Otto Hahn and Fritz Strassmann were probing the secrets of the uranium atom. Like Rutherford, they used atomic bullets. They used neutrons, the neutral particles that were discovered hidden in the nucleus of the atom. The neutron is an ideal bullet. Since it is neutral, it isn't deflected by the electrical charge of the atoms and flies through them in a straight course. Finally, it struck a nucleus. The uranium nucleus split in two. Atomic fission had been accomplished. But this wasn't all that happened. 2 neutrons were released from the split nucleus. 1 bullet was used to split the atom, and 2 new ones were created in the process. Now we have 2 neutrons to split 2 atoms. This implied a fabulous prospect, a nuclear chain reaction in uranium. Let's go back to our mousetrap atoms. We can create a chain reaction with them. We'll use our 2 ping pong balls for neutrons. They will be released when the atom splits. Now all these mousetraps are the atoms that will be in the game. They are set, loaded, and ready to go. To start the chain reaction, all we need is 1 neutron. It has to trigger just 1 trap. The ping pong balls that are released will set off 2 other traps. And then we'll have 4 balls flying to trigger more traps. I think you can see what is going to happen. Watch. An atomic chain reaction works in exactly the same way. 1 neutron is enough to start it. The atomic genie was freed, and his devastating force posed a fearful threat. The world was deeply shocked by the first atomic explosion. We all wondered if atomic energy had better remained a secret forever. We are like the fisherman. When he first beheld the frightful form of the genie, he too wished that he had never found the vessel.
Know that presently thou wilt have to die.
Heaven forbid!
But our fable had a happy ending. The fisherman had his means of making a friend of his enemy. And fortunately, science has its way of doing the same thing. An atomic blast is more than a threat. It is also a regretful waste of heat and radiation. To make this energy useful, the explosion must be slowed down. Let me show you what I mean. Our mousetrap explosion can be slowed down with the aid of a slow-motion camera.